The next speaker is Jonatan Vignatti from Santa Maria Technical University. He will be talking about RGE effects on lepton-flavor violating neutral meson decays.
Yes, good morning, everybody. My name is Jonatan Vignatti, PhD student in the physics department of the main university. Today I'm going to talk about this renormalization effects on lepton-flavor violating neutral meson decays. So this is the outline. I will be talking about a little introduction, motivate why we're interested in lepton-flavor violating in these processes. Then how renormalized QED, QCD can improve the Wilson coefficient that are involved, and that pretty much the outline. So let's go to the introduction. So we know that the standard model it's a great theory, but it's a framework that explains most every force, except for gravity. We know that description of this this description of nature is incomplete because it doesn't consider, for example, the mass of neutrinos. We know that from experiments that neutrinos have mass because it was observed that neutrino oscillates, and this lead to lepton-flavor violation for neutrinos. Another examples are mu electron conversion in nucleus, decay mu electron gamma. And let's pay attention to this decay, for example, to see why standard model at 3 level doesn't have lepton, doesn't allow lepton-flavor violation, but at one loop one can see that actually it appears lepton-flavor violating, but the branching ratio is strongly suppressed to the order of 10 to the minus 54. The branching ratio is related to the masses of the neutrinos. That's why neutrinos need to have mass. The mixing matrices that mix leptons and neutrinos. So so let's go to lepton-flavor violating effective Lagrangian that we work according to this paper in the footnote. So we consider this effective work lepton-flavor violating Lagrangian with operators up to 6 dimensions. We have the classical currents from leptonic and for quarks currents, and with the coefficient Wilson coefficients with parity defined. So this ij could be scalar, so the scalar vector, axial vector, and tensor, and the c's are the Wilson coefficients. So we're interested in processes like this. So trivial lepton-flavor violation decay, because with this decay we know the experimental branching ratio that could set up upper limits to this process. Above all, this can set up upper limits to the meson decays. For example, in the second part of this, from this diagram, one can see that first this lepton is decaying into 3 values. Lepton, it could be two gammas or 2 leptons, but the second part is the meson decaying into 2 leptons or 2 gammas. In this case, it could be vector. In this case, for exact example, we use pseudo-scalar decay. So the next is how we put some limits on meson decay. For example, take the neutral meson decay to mu electron. We have from the experiment the upper limit to branching ratio for this process that is around this order. So for any pseudo-scalar meson decay, we can generalize. We know that from this upper limit branching ratio, we can set up a upper limit to the decay width. The decay width that has this pseudoscalar meson decay. So considering that this decay width is a function of the coefficients, Wilson coefficients, we can set up upper limit for these Wilson coefficients. So that's why this is how we connect experiment and this phenomenological any phenomenological model. So the Wilson coefficient is related to this lambda that has energy energy dimensions. So this is this lambda is the scale that lepton-flavor violates. So but let's see how this QCD QED QCD can improve the Wilson coefficient. So this Lagrangian that I first showed could be rewrite in chiral base operators, because in effective field theory that we use, this is the classical quarter lepton lepton-flavor violating in chiral base. So these operators have this form, and one can see that that these operators contain information about the lepton and quark currents for scalar tensions and vectors in this case. So we can see that this the meson decays that I was talking about in the first in the 8th slide. This meson is meson decays into leptons or gamma gamma. This case in decaying into leptons. We must remember that meson is composed of two quarks, quark antiquark, and the correction we are making in this vertex. So what this correction is on one loop. The general form of the corrector operator matrix is given by this, and there we need to renormalize this operator, and the renormalization and this renormalized operator is in function of this Z QL the Q again for QCD. It is from correction to the fields. All these guys comes from the normalization, renormalized fields, and this CIG appears to cancel for the cancellation of singularities. So in order to cancel to require the cancellation of singularity, one finds that the form of CIJ has this form from QCD and for QED. Hence, we can calculate the anomalous dimension in the minimum subtraction scheme, and the anomalous dimension has this form according to this paper of yours. This is pretty much used. So the loop in one loop QCD anomalous dimension are diagonal, but the more interesting are the matrices that are not diagonal. For example, this one for QED correction in chiral defined base, left, left, right, right, has this form. So the other QED anomalous dimensions are just numbers, but are going to correct. But the in the mixing, we can say that this matrix is important because the elements that are off the diagonal are represented the mixing under renormalization. This comes from operator mixing, and this is going to improve, enhance the coefficients that were calculated before that. I show you how to set up limits to the first Wilson coefficients. So we use a classical Wilson coefficient renormalization group equation for the Wilson coefficient that is here. And up next, we show that this coefficient, this equation can be solved in this way, that has a component from QED and QCD and QED. And the evolution matrices takes a form from QCD. This is mostly it's pretty much known, these results, and the for QED have this form. Is all this in taken from this paper, the solutions, and we need now this to put some numbers to actually see how the numbers are improved from the Wilson coefficient that we want to improve. So this finally there. Let's see how this renormalization group equation induce better limits on the Wilson coefficient. So with numerical values, we have in the beginning that we calculate. I show you how to do this. In Wilson, friction ratios correspond to from the experiment correspond to Wilson coefficient. So this is called a coefficient experiment from experiment, and this matrix evolution matrix are known because we're going to take we're going to get values, numerical value for this. We're going to get matrix, evolution matrix for you. So this is known, and this is known. So we have to just clear this new Wilson coefficient, CJ. For example, if I have, if I have this Wilson coefficient evolution matrix for you, let's say you you do, let's take 4 times 4 U evolution matrix. One has to do this. And how can I find the new enhanced Wilson coefficient C1, C2, etc.? So we can just take this first term and neglect the others and just clear C1. So this guy goes down, you know, basic arithmetic, and that's why that is the way that we can find this signal. But pay attention to the Wilson coefficient at the beginning. We change the basis to the chiral operators. So for each Wilson coefficient, we're going to have at least 4. We're going to express in a combination of 4 Wilson coefficients that has chiral base or chiral defined, left, right, and all the combinations. So finally, where these are the numbers. So the first column correspond to without QED, QCD, the third scale. So for example, we can see that axial, vector, axial, at the beginning, it doesn't mix. That's why it has this number. But with QED, QCD, at the upper energy around 1 TeV, one can see that it's enhanced because this matrix with this axial vector mix, and we can see from passing from 2.2 to the order that 10 to the 1000. So one can see why these improve like 3 orders of magnitude, from 2.2 to the hundreds, right? So that's because these two guys are mixing from the operator mixing that comes from the all the matrices that are not diagonal. So this is the other guys. This was for the axial vector. This was for the scalar or pseudo-scalar and all the mixings. And the results, we can see something interesting because this is for tensors. And we can see that when at the beginning, the first column corresponds to the without QCD, and the second is with QCD, QED corrections to the 1 and 10 electron volt. So we can see that some at the beginning we have no limits. Okay, thank you. At the beginning we have no values, and it's, with the mixing of this little correction, one can have new values that at the beginning we have at the beginning limits for this lambda that translate into the Wilson coefficient. So let's summarize this. We found that QED correction are particularly important due to operating mixing. Let's see, as I told you before, the AA-BA coupling can become more sensitive because of the mixing. At the beginning, it doesn't mix. So the bounds for scalar scalar couplings are also tightened up to order of magnitude, as I show you in the tables. And for the limits, the tensor is mostly from QCD. QCD has one loop correction, so this just has diagonal matrices. So the correction is just multiplication numbers. So the operators are slightly weakened. Our constraint can be useful for further studies for phenomenological implications for the effective lepton-flavor violations effective theories, and its ultraviolet compression. So thank you for listening.
Thank you very much for the nice exposition. Is there any question? Okay, I have one short question concerning the QCD part. I understand that this mu, lower energy, at low energies, electromagnetic coupling has no problems there, but the QCD coupling does. It has Landau singularities, so you cannot go too low with the mu, lower energy. How low did you go there?
The energy scale?
Yes.
From the energy scale, we are from the lowest is I can put it is around 1 GeV because of the QCD perturbativity, and the upper scale is 1 TeV. So these guys are running from 1 TeV to mu that is 1 GeV.
Yes.
That's the energy that we consider because of perturbativity of QCD.
Mm-hmm. Okay, to 1 GeV, yeah, because lower than that you cannot go because of this Landau singularity problems also. Claudio Deep has another question. Please go ahead.
Yes, Jonathan, you showed there that some of these coefficients they grow like from like a number 2 to like 2 orders of magnitude larger, right?
Yes.
And for example, yeah, like the one in the second line there or something. And can you show exactly where? I mean, where in your calculation, where what operator is this that gets such a huge enhancement?
Okay. Yes.
What's the process itself? Because it could be suspicious that something could be, you could have the need of going further in the expansion because such a large effect only to one loop is, something you should care about.
Excellent question. Well, this is the most interesting, and it relates the evolution matrix that has mix all these Wilson coefficients. Obviously, we need to see this evolution matrix that I has this after this. So these are how the Wilson coefficients mix in the chiral operator base, and these are the matrix. For example, let's see, this is for scalar, scalar, and tensor, how they mix Wilson coefficients, and let's see why. For example, these vector axial coefficient mix among themselves only to axial to vector. So let's see in this table that axial, and vector coefficients are mixing actually according to the matrix mentioned in the last slide. Let's remember axial, vector. So let's see this. We got what we got from the numbers. We actually going to get that this is going to be the matrix that mix coefficient Wilson coefficient and axial and vector. So we see that this matrix is not diagonal. So of diagonal I made it. For example, in vector axial with this vector. This is the Wilson coefficient, and let's remember that axial is 2.2 and vector is around without QCD is around 10 to the 1,000 order of magnitude. So multiplying these guys, we have indeed hundreds. That's why it is the big infants appearing here. So this is the most thing. But call orientation. So this is a work in progress, but this is the final results mainly. That's why the
yeah, I understand that, but it's fine. You should exemplify the with the diagram where in the process when you have this correction in the diagram, where is the process enhanced? This is it would be useful for you.
What diagram? Excuse me.
What so well, you have to have a process here, right? You for example, you were looking at well, muon to E gamma, whatever process you want. You should take one example of a process and see where these operators enter and see how they mix and what this huge enhancement appears. This.
Yes, it is indeed in these slides. One can see that obviously these operators are going to mix, and because how do we know that actually mix? because I'm not showing this in this slide because of these operators. According to these definitions of anomalous dimension, are going to mix. We see that this mixing transcends to the anomalous dimension from QED, because this accounts for mixing for operators. So I'm not showing the operator mixing explicitly, but under renormalization, this anomalous dimension shows that actually are a mixing because we have non-element matrix element that are non-diagonal. That but in the paper, obviously, obviously there are mixing. We show the mixing operators. So it's there in the contained here.
Okay, we are short of time, but one short question from Mauro Cambiaso still, please.
Yeah.
Yes, it's Marcelo who wants to raise a question.
Yes, okay, yes, please.
Thank you. I had the same question from Claudio, so it's very nice. Thank you.
Okay. Okay, so if there are no other questions, then let's thank the speaker again. Thank you very much for your nice presentation.